So we have seen that the wave equation is directly derived from Maxwell equations, and we can consider, just to simplify a little bit, the one-dimensional case. Let's keep going with this one-dimensional case, and we just consider the existence of a wave propagating along the positive axis. Well, in that case, it's very simple to prove that if this is the electric field, this has to be the magnetic field. Notice the electric field has X component and the magnetic field has Y component, so they are orthogonal. And also their amplitude, they are proportional, and their magnitudes are just related by this value, the square root of epsilon over mu. Remember that epsilon and mu depend on the medium in which we are, and this is known as the medium impedance. In the case of free space, it has a value of 120 pi ohms. So notice that electric and magnetic field are not independent when we're talking about this electromagnetic wave. That particular case, which is not general, because remember that we are considering the one-dimensional case, we are talking about what is known as a transverse electromagnetic wave, or TM wave. Why it's called transverse? Because the field components, electric and magnetic field, are perpendicular to the direction of propagation. So the fields are transversal to the direction of propagation. Remember that also electric and magnetic field are not independent, they are linked through Maxwell equations. And also, just a word of caution, not all solutions, not all waves have to be TEM. There are other solutions, as we'll see later on. Now, for that one-dimensional case means that if I have a certain field, and imagine that this is the electric field, those red arrows, that's the representation of a field that has a certain space variation and a certain time, t equals t naught, and this is the vector. The magnetic field is directed along the y-axis and is proportional. They are related by this medium impedance. And after another time, t1, what we will have is that that wave will have traveled, it will have moved along the z-axis, and it will have traveled a distance d. And of course, that distance is given by the time difference and the propagation speed, the propagation velocity. Propagation velocity, that if we had seen before, depends on the media, and for free space is the well-known speed of light. So this is the situation we have. Now, remember that any field solution for the wave equation has to respond, in the one-dimensional case, has to respond to these equations, and we want to see in more detail why is that coupling between the electric field and the magnetic field that give rise to the wave phenomenon. For that, we are going to use a very well-known numerical method, which is known as the finite difference time domain, or FDTD, that will allow us to show numerically that wave equation. Now, the first thing what we do is that we will approximate the space derivative and the time derivative of the fields by what we will call the finite difference. What is the finite difference? Well, that space derivative, we can approximate it by just the difference of the field in two very close places in space, just two positions changed by this delta z, and then of course dividing by that increment of space. And that's a good approximation for the space derivative. Also with the time derivative we can do the same thing. We just make the difference of the field value into time samples, and dividing by that time increment we have a good approximation of the time derivative of the electric field. We are going to use a shorthand notation. If we discretize the field along the z-axis with a certain step delta z, we can write any position as k, where k is an integer number, times delta z. If we use this index k to denote a position, we can write those finite differences in that shorter way, and this is just for convenience. We use the shorthand notation just to make things simpler. Well, we can do similar thing for the magnetic field, but for that we're going to use what is known as the G's grid. G's grid, it has its name after K and G. We proposed a robust FDTD algorithm in which the two fields are interlinked through the sampling grid. We will not sample the magnetic field in the same positions as we are sampling the electric field, but remember that we were sampling the electric field at these positions, K delta Z. We're going to sample the magnetic field at positions K delta Z plus delta Z over 2. So we are sampling in different positions, and also in time we are sampling the magnetic field at different time instances that we are doing for the electric field. So if we try to depict this, imagine that we have a certain electric field and we sample the field in certain space positions. We're going to sample the magnetic field in those intermediate positions that are between two samples of the electric field. So the time, the derivative of the magnetic field will be approximated by these finite differences, in which the only difference is that the sampling points are different than the ones we are considering for the electric field. Okay, so having this in mind, we can write these equations, which remember those came directly from Maxwell equations. We can write them in what we will call this discretized form, if we are just substituting those derivatives, but those finite differences. But they're just, if you want, there's some sort of approximation, some numerical approximation to those mathematical equations. Now, once we have written these equations, we can find an algorithm to compute the field, how the field will change along time and space. So what we'll do is first we consider that the field is 0, that's our starting point, and we'll consider this a certain excitation. That means that in a certain position Z, we will be forcing a certain value of the field. And the question is, how will the fields evolve from now on? Well, that's very simple, because from those numerical expressions we have, we can derive this expression, in which we can find that the value of the field in position K at a certain time t plus delta t has the following value. This term here, this is the excitation, which is the field we are forcing in position K and time t, plus this term here. But of course, initially that term is 0, because we were saying that initially the fields were 0, so the magnetic field is 0. So actually, well, little change. We are essentially assuming that at the next time interval, the field has essentially not changed. Let's see what happens with the magnetic field. Well, for the magnetic field, we have this expression here, and now, well, this is true that this is initially 0. This term is initially 0, but this is the excitation term. So the magnetic field, now the next time interval for which we are computing the magnetic field, it has changed. So now we can just loop the process for all positions on time interval, and we'll see how the electric and the magnetic field will change with time and position. Now, this is very simple to implement numerically, so let's see just a final result of this implementation. So we're assuming that at a certain position, z equals 0, we apply the following field. So this is a Gaussian modulated pulse. That shape is essentially a Gaussian function, and well, we have a certain modulation here, and you can see that the overall duration of this pulse is about 1 millisecond. Okay, so this is the field we will be forcing at our starting position. We apply the FDTD algorithm to compute at each time interval how is the electric and the magnetic field. Okay, and see, this is the result. We're going to show you just an animation in which this is the position, Z. We are starting by forcing the field, remember, at the position Z equal 0 at the origin of coordinates, and let's see how the field, will evolve with time. Now, this time computation that we're seeing is each iteration we do in the loop. And we can see that we get this sort of result. Actually, we can see that this is a traveling wave. We can see the electric field traveling. It's essentially the same field what we are forcing at the origin, that it's traveling along space. We can see that the magnetic field has essentially the same shape. Notice that here we're plotting the electric field, and here we're plotting the magnetic field multiplied by the medium impedance, 120 pi. So once we do this multiplication, we can see that the two of them have the same value. And if we look, for instance, after a while, for instance, this at this time, that will be 1.5 milliseconds, and we see that the distance traveled by the pulse, remember that at our starting point the pulse was 0, so essentially this is the distance traveled by the pulse. We can find the velocity, and we see that actually the velocity at which this wave is traveling is what we would expect. And we also realize that electric field and magnetic field are related to this constant. So the important thing here is that we have obtained this result just by numerically solving this set of equations. And we see that all our expected results, that is, having a wave traveling at the speed of light and having that relationship between the electric field and the magnetic field, are true. And remember, it all came from these equations, and as I mentioned before, is that interrelationship that we have between electric field and magnetic field that actually gives as a solution that wave that somehow is self-supporting electric field and magnetic field and are able to travel in space. Now, the important thing is also finite difference time domain method. It's a numerical method used in many applications, solving many electromagnetic problems. And I will just show you something. What would happen if, once I have this wave propagating, we put a conductor at a certain position? Well, we know that this conductor, this metal, will force certain boundary conditions, and those boundary conditions are that the tangential value of the electric field has to be 0. So that means that where we put this conductor, the electric field has to be 0. Well, we have just taken the same algorithm we had before, and we are just forcing that in a certain position. In that case here, when we have that red line, we are forcing that the electric field has to be 0. Now, that's the only thing we do. We just, at each iteration, no matter what the value is, we force here the value of the field to be 0. And let's see how, what would be the result of applying this FDT, what would be the result of applying the FDTD algorithm. Now, we have the wave. Now, remember that this red line is the conductor. We are incident to this conductor, and see now that there is that behavior here. Actually, well, some strange things are going on. But what we have is that after we have the wave incident to the metal conductor, we have the wave being reflected, and we have essentially the same wave traveling now in the opposite direction. And notice, we have not done any math. We have just taken the algorithm, we have placed the boundary condition, which is the value of the electric field in that position, but we know that has to be 0, and we have obtained the numerical solution for that.